There is a rock flying toward Earth right now, and nobody knows how big it is. Not an estimate, not a range. A blank field in an official NASA database, attached to an object discovered just days ago, already close enough to matter. It is about to pass Earth at twice the distance of the Moon, one of the closest flybys of this entire year, and it is doing it anonymously, without a size, without a mass, without any of the numbers that would tell you what it would actually mean if something went slightly wrong, and it is not alone. This week, 21 asteroids are on the close approach list with 0 diameter estimates between them. 3 of them buzz past within 48 hours of each other. So here's the only question that matters. If this is what we can see, what exactly are we missing? Stay until the end, because what we are not seeing is the actual story. Subscribe and stay close, because the catalog is still being written. 21 unsized objects this week alone, 3 of them clustering in 48 hours, and a detection network that still cannot watch the sunward sky. Those are not problems being ignored. They are problems being worked on, slowly, with real instruments and real missions. When the answers start coming in, this channel will be the place, breaking them down. You want to be here for that, not catching up later. There is a rock flying toward Earth right now, and we have no idea how big it is. Not because nobody is looking, not because we forgot to check, but because the universe does not always give us enough light to work with, and this particular rock decided to announce itself only days before its closest approach, leaving astronomers with detection data but almost nothing else. No size, no mass, no reliable estimate of what would happen if the trajectory were even slightly different. Just a point of reflected sunlight on a telescope image, moving fast, logged in a database, and quietly added to a list that most people will never read. The asteroid in question is about to fly past Earth at roughly twice the distance of the Moon. That sounds like a comfortable margin until you understand what that distance actually means at these speeds, with this level of uncertainty baked in, and with a size field in the database that is completely blank. Twice the lunar distance sounds safe, and statistically, it probably is. But the fact that we are making that probabilistic argument about an object we cannot yet characterize tells you something important about where our planetary defense system actually stands right now. When astronomers publish close approach data, they are reporting 2 very different kinds of knowledge, and the gap between them rarely makes the headlines. The first kind is orbital data, where the object is, where it is going, how its path curves through the solar system. This information stabilizes relatively quickly. Even a short observation arc of a few days can constrain an orbit well enough to rule out a collision. The second kind of knowledge is physical characterization, how big the object actually is, how reflective its surface is, what it is made of, how much mass it carries, and therefore how much energy it would release if it ever did intersect with something it was not supposed to. That second kind of knowledge takes much longer to develop. Sometimes months. Sometimes it never comes at all, because the object moves out of observing range before anyone gets a good look. The term astronomers use for intrinsic brightness is absolute magnitude. It tells you how bright an object would appear at a standardized distance, but brightness alone does not give you size. 2 objects can share an identical brightness reading and differ in physical diameter by a factor of 10 or more, depending entirely on how reflective their surfaces are. That reflectivity is called albedo, and it varies enormously across the asteroid population. A dark, carbonaceous rock will absorb most of the sunlight hitting it, making it appear smaller than it actually is. A bright, stony body will bounce light efficiently and look larger than something with similar mass but different composition. The brightness number tells you a rock exists and gives you a rough bracket. It does not tell you what you are actually dealing with. This week, that bracket is disturbingly wide for 21 different objects on NASA's close approach list. 21 asteroids making notable passes by Earth and not one of them has a published diameter estimate. That is not a fluke. That is a pattern, and it is a pattern worth paying attention to. What makes this particular flyby even more interesting is that it is one of 3 unsized objects passing within close range of Earth within a 48-hour window. 3 rocks with unknown dimensions buzzing past the planet in under 2 days. All discovered recently, none of them characterized. Individually, each one could be written off as routine. Statistically, the close approach list sees lots of small, uncatalogued objects. But 3 in 48 hours, all without size data, all newly found, that clustering raises questions. Are we seeing a genuine uptick in detections from improved survey systems? Are we catching the edge of something larger we have not fully mapped yet? Or is this just the normal noise of a solar system full of debris that we are only now becoming sensitive enough to notice? The uncomfortable truth is that orbital certainty and physical knowledge do not arrive together. We can be highly confident about where a rock is going while knowing almost nothing about what it would do when it arrived. The math of orbital mechanics is elegant and well understood. The photon counting problem of trying to extract size information from a faint, fast-moving point of light is messy and often unresolvable without additional resources that may not be available in time. So we end up with precise trajectories attached to unknown objects, and that combination, confident paths, unknown payloads, is exactly the kind of information gap that deserves more attention than it typically gets. And here's the thing that should stay with you as we go further into this. The absence of data in that diameter field is not carelessness. The people running these systems are meticulous. It is a hard limit imposed by physics, by telescope time, by the geometry of a given object's approach. We found it. We tracked it. We just could not see it well enough. And if we could not see it well enough, the obvious question becomes, what else is out there that we have not found at all? The phrase, twice the moon's distance, does a lot of work in asteroid headlines, and almost none of that work is making things clearer. Here is what it actually means in raw numbers. The moon orbits Earth at an average distance of roughly 384,000 kilometers. Twice that is approximately 768,000 kilometers. That is the gap between this rock and the surface of the planet at closest approach. In human terms, that sounds enormous. In solar system terms, it is a near miss at highway speeds, a whisper across the void, a proximity that would have been front-page news a century ago and now barely registers as a footnote in a database that refreshes daily. The reason media outlets reach for lunar distances as their unit of measurement is that it sounds vivid. The moon is something people understand intuitively. We can look up at it. We know it is close. So framing an asteroid's approach in terms of moon distances creates immediate emotional resonance. This thing came within 2 moon lengths of where you are standing. That resonance is real, and it is not wrong. But it strips away context that matters enormously for understanding what that distance actually implies. To put it differently, consider where our infrastructure actually lives. Geostationary satellites, the ones handling your television signals and weather forecasting, orbit at about 35,000 kilometers above Earth's surface. The International Space Station rides at roughly 400 kilometers up. Low Earth orbit, where most operational satellites live, spans a band between about 200 and 2,000 kilometers. Against those numbers, 768,000 kilometers sounds almost casual. It is more than 20 times farther out than geostationary orbit. So how can it simultaneously be described as a close call? The answer is scale relativity. Compared to the average distance between Earth and even the nearest other planets, this is extraordinarily close. Compared to your living room, it is not close at all. The framing you choose completely determines the emotional weight of the number, which is why journalists and scientists often end up talking past each other. They are using the same figures to evoke completely different contexts. But here's where it gets genuinely interesting, and why the distance alone is not really the point. A small fraction of asteroids in any given year do pass closer than geostationary orbit. Some pass closer than the ISS. In 2025, an object designated 2025 TF flew through inside the orbit of many satellites before anyone had detected it at all. It was found after its closest approach. That is a category of event that deserves a different kind of conversation than twice the moon's distance. It is a category of event that says our detection window sometimes closes after the rock has already come and gone. There is another layer here that rarely makes it into popular coverage, and that is the concept of Earth's Hill sphere. This is the region of space within which Earth's gravitational influence dominates over the sun's pull. Objects passing through this zone are meaningfully affected by Earth's gravity, and at close enough approaches, an asteroid's trajectory can be bent in ways that change its future orbital path significantly. A flyby that seems safe today can scatter into a different orbit, one that might intersect with Earth on a future pass years or decades later. This is where gravitational keyholes become relevant. A keyhole is a tiny region of space, sometimes only a few hundred kilometers wide, that an asteroid must pass through during a close approach in order for gravity to redirect it onto a collision course during a later orbit. These keyholes are invisible. They are mathematical constructs defined by the geometry of a given trajectory. And at twice the lunar distance, with trajectory uncertainties still present, there is always a non-zero probability that the refined path passes through one. Usually, that probability collapses to nothing with better data. But the window between rough trajectory and refined trajectory is exactly when you do not want to be making confident public statements. And it is exactly when the objects tend to generate the most dramatic headlines. So when you read twice the moon's distance in a headline, here is what it might more honestly say. We found this object recently. We know roughly where it is going. We do not know how big it is. And there is a period of hours to days where the combination of distance uncertainty, size uncertainty, and trajectory uncertainty creates an information profile that is genuinely incomplete, not catastrophic, not a crisis, but incomplete in ways that matter, in ways that would cost energy to resolve, and in ways that are being quietly accepted as normal across a close approach list that currently includes 20 other objects in the same condition. The close approach list that NASA maintains is one of the most genuinely useful and quietly alarming documents in planetary science. It is a rolling catalog of objects that will make notable passes by Earth, updated as new observations come in, populated with trajectory data, orbital uncertainties, and, when available, size estimates. The "when available" part is doing enormous work in that sentence. Because for a significant fraction of the objects appearing on that list in any given week, the size column is simply empty, not marked as uncertain, not populated with a wide range, empty. This week, that empty column appears beside 21 different entries, 21 close approaches, 0 diameter estimates, and that is not an anomaly. That is Tuesday. To understand why size estimates lag so far behind orbital data, you need to understand how the major survey systems actually work and what they are optimized to do. Pan-STARRS, the Panoramic Survey Telescope and Rapid Response System, scans vast areas of sky looking for moving objects. The Catalina Sky Survey does similar work across different sky regions. ATLAS, the Asteroid Terrestrial Impact Last Alert System, is specifically designed for rapid detection of objects on final approach. These are extraordinary instruments, and they have dramatically increased the rate at which humanity finds small solar system bodies, but they are optimized for discovery, not characterization. They are built to find the points of light and log their positions over time, which is exactly what you need to calculate an orbit. Actually determining what that point of light physically is requires something else entirely. Size, as astronomers typically calculate it for an asteroid, is inferred rather than directly measured. The inference works like this. You observe the brightness of the object over time. You assume or estimate its albedo, how reflective its surface is. You combine those numbers and work backward to a diameter estimate. The problem is that albedo across the asteroid population varies enormously, ranging from highly reflective stony bodies all the way down to carbonaceous objects so dark that they absorb light almost like flat black paint. A single asteroid with an unknown albedo could plausibly have a diameter anywhere within a range of several 100% without violating the brightness data you have. That uncertainty does not shrink until you get follow-up observations under specific conditions, or ideally radar imaging or infrared data from a space-based instrument. Observational geometry adds another layer of difficulty. The angle between the sun, the asteroid, and the observer, called the phase angle, affects how much light the surface reflects toward you and changes the apparent brightness in ways that have nothing to do with the object's actual size. The time of observation in relation to the object's rotation matters. The distance matters. Whether the object happens to be showing you a broad face or an edge matters. An asteroid that looks bright in one observing geometry might look substantially dimmer in another, and both observations are technically correct. Without multiple observations across different geometries, the size inference is genuinely unreliable. This is why some objects are only discovered after their closest approach. 2025 TF, which has been mentioned in connection with this cluster of flybys, was found after it had already passed within the orbital zone of operational satellites. The discovery came from archived images. The object was identified in retrospect, after the approach had already happened. That is not a failure of any individual observatory. That is the reality of trying to watch an entire sky with a finite number of instruments pointed in directions constrained by the geometry of sunlight and orbital mechanics. What this means at scale is significant. Last year, approximately 176 objects passed within the lunar distance. Most were small. Most posed no threat. But the number that were detected before their approach, characterized to any meaningful degree, and tracked continuously from discovery through closest approach, is a much smaller subset of that total. The population we are cataloging is almost certainly not the full population of objects making these passes. It is the fraction of that population that happened to fall within our detection geometry, at the right time of year, at a bright enough magnitude, from a direction our telescopes could actually point. The broader implication follows directly from that. If the detected population is a subset of the real population, then the undetected fraction contains an unknown number of objects of unknown size. Some of them will be small and harmless. Some of them will be larger. The distribution of sizes across the full population follows a well-understood power law. Smaller objects massively outnumber larger ones, but that statistical comfort only applies if you believe your sample is representative. And this week's 21 unsized objects suggest that the sample has edges we are not fully seeing. 3 rocks, no size data, 48 hours, and a solar system that does not announce its plans. The clustering of 3 newly detected unsized objects within such a tight window is the kind of thing that probably has a mundane explanation, and that mundane explanation is probably worth taking seriously before jumping to anything more dramatic. Survey systems detect objects in bursts tied to observing conditions, weather windows, and the specific geometry of the sky on a given night. When conditions are good and a survey system is running efficiently, detection rates can spike. Improved algorithms, better processing pipelines, more telescope hours, any of these can create a temporary uptick in discoveries that looks like clustering, but is really just an efficiency artifact. That is probably the most likely explanation for 3 unsized objects appearing in close proximity on the approach list within 2 days. But probably is not certainly, and the history of science is full of patterns that were dismissed as noise before they turned out to be signal. So it is worth asking what other explanations exist, not to endorse them, but to understand what they would imply if true. Detection bias is one of the cleaner explanations worth examining. Telescopes that hunt for near-Earth objects face consistent geometric constraints that create blind spots in the sky. The most significant of these is the region close to the Sun. Objects that approach Earth from the sunward direction are essentially invisible from the ground because ground-based telescopes cannot safely or effectively observe near the solar glare. The Chelyabinsk meteor in 2013, the airburst over Russia that injured more than 1,000 people and shattered windows across a wide area, came from a sunward direction. Nobody saw it coming, not because the detection network failed in any mechanical sense, but because the sky geometry made it fundamentally undetectable from the available instruments. The rock came out of the part of the sky we cannot watch and arrived without warning. Near the lunar cycle boundaries, when the moon is full and its reflected light washes out faint objects across a large region of sky, detection rates drop for dim, fast-moving targets. The moon's glow is not dramatic in the way solar glare is, but it represents a consistent suppression of sensitivity that can mask objects that would otherwise be marginal detections. A survey operating during high lunar glare conditions will miss a predictable fraction of the faint population. Then, when lunar conditions improve, there can be a catch-up period where objects that were marginally detectable before suddenly become visible. That catch-up could look like a brief cluster of new discoveries. The more exotic possibility, genuinely speculative and worth flagging as such, is that objects appearing in tight temporal clusters could reflect physical clustering in the asteroid population itself. Fragmentation events, where a larger body breaks apart under tidal stress or collisional impact, produce families of objects on similar orbits. These families are well documented at larger scales. Whether the tight timing of these three objects reflects any kind of physical grouping would require detailed orbital comparison, calculating whether their trajectories share a common ancestry. That work has almost certainly not been done yet, and may not reveal anything interesting when it is. But the question is scientifically legitimate. There is also the concept of meteoroid stream association, the possibility that small objects detected near Earth are related to known or unknown cometary debris trails. When a comet passes through the inner solar system repeatedly, it seeds its orbital path with particles and fragments that spread out over time into streams. When Earth's orbit crosses one of these streams, we get meteor showers. But larger fragments within such streams could, in principle, appear as a series of objects on similar approach trajectories within a short window. This is highly speculative for any given cluster of detected objects, but it is not a physically impossible scenario, and it is the kind of hypothesis that planetary scientists would test given the right orbital data. What all of these explanations have in common is that they point toward something larger than the three objects themselves. Whether the clustering is a detection artifact, a lunar cycle effect, a fragmentation signature, or something else entirely, it is a reminder that the close approach list is not a comprehensive inventory. It is a snapshot of what we can currently see, filtered through the specific conditions and capabilities of the moment. The objects we can see are teaching us, indirectly, about the geometry of our own blind spots. And those blind spots are not randomly shaped. Something out there is moving through our neighborhood. We found 3 of them this week. The question that should follow you into Act 2 is a simple one. How many did we miss? There is a direction in the sky that our planetary defense network essentially cannot see, and every rock that comes from that direction arrives without warning. That direction is toward the sun. It seems obvious when you say it out loud. Of course, telescopes cannot point at the sun. It would destroy the instruments. But the practical implications of that constraint for asteroid detection are genuinely severe and surprisingly underappreciated in public discussions about planetary defense. The sunward hemisphere of the sky, the half of the celestial sphere centered on the direction of the sun, is largely inaccessible to ground-based optical surveys. And because asteroids on Earth-crossing orbits can approach from any direction, a meaningful fraction of the potentially hazardous population can only be detected when it has already passed its closest approach point and is moving away from us. By then, the flyby has already happened. The Chelyabinsk event is the canonical example of what this blind spot means in practice. On February 15, 2013, a rock estimated at somewhere between 17 and 20 meters in diameter entered Earth's atmosphere over southern Russia and exploded in an airburst at an altitude of roughly 20 to 30 kilometers. The energy released was equivalent to approximately 500 kilotons, more than 30 times the yield of the atomic bomb dropped on Hiroshima. Windows shattered across a wide region. A zinc factory roof collapsed. More than 1,500 people sought medical attention, most of them from flying glass. It was the most energetically significant impact event in over a century, and nobody saw it coming. The reason nobody saw it coming is not that the detection network was asleep. It is that Chelyabinsk approached from the sunward direction, in daylight, from a part of the sky that ground-based telescopes cannot surveil. The rock entered the atmosphere from the east, coming in at a shallow angle that meant it was in the sky for a relatively long time before it detonated, and still nobody detected it in advance because the instruments that could have found it were pointing at the night side of the planet, away from the sun, scanning for objects in the exact opposite direction from where this one came from. Ground-based optical surveys are fundamentally constrained by the day-night cycle. They observe the night sky, which means the hemisphere of space opposite to the sun. They also tend to avoid the regions near the horizon and near the Milky Way galactic plane, where sky background light reduces sensitivity. These constraints create predictable gaps. A telescope in Chile watching the southern sky on a clear night is doing excellent science, but it is structurally blind to anything approaching from the sunward direction during that same night. No amount of improved sensitivity or wider field of view changes that geometry. The solution that planetary scientists have been working toward for years is space-based infrared detection. An infrared telescope in space, positioned between Earth and the Sun, could watch the sunward hemisphere continuously, detect the thermal emission from asteroids rather than their reflected light, and, crucially, provide size estimates based on heat output rather than albedo-dependent brightness. Heat is a much more direct proxy for size than reflected light, which is why infrared observation cuts directly through the albedo uncertainty problem that makes so many close-approach objects impossible to characterize from the ground. NASA's NEO Surveyor mission represents exactly this kind of capability. It has been in development for years, designed specifically to address the sunward detection gap and to dramatically accelerate the discovery of near-Earth objects in size ranges that current surveys consistently miss. The mission has faced budget pressures and scheduling changes that have pushed its timeline, but the scientific case for it remains clear, and the engineering basis is solid. A space-based infrared survey would not just find more objects. It would find the ones we currently cannot see at all. The ones coming from the direction of the sun. The ones too dark to reflect enough visible light. The ones that currently arrive without warning because our entire detection infrastructure is pointed the wrong way. And until that capability is operational, every rock that approaches from the sunward direction remains in the category of things we are hoping to get lucky about. The blank diameter field in an asteroid database entry does not mean the object is small. It means we do not know. Those are very different statements, and conflating them is one of the most dangerous assumptions in casual discussions about planetary defense. The entire problem traces back to albedo, the reflectivity of an asteroid's surface, and the way reflectivity interacts with what we can measure from a distance. When a ground-based telescope detects an asteroid, what it is actually measuring is the amount of sunlight that the rock reflects back toward the detector. That measurement, combined with the known distance to the object, gives you the absolute magnitude, the intrinsic brightness of the body. If you then want to convert that brightness into a diameter estimate, you need to know how much of the incoming sunlight the surface is reflecting. And that number varies across the asteroid population by a factor of roughly 10 or more. At one extreme, the brightest stony and metallic asteroids reflect somewhere around 50 to 60% of the light hitting them. At the other extreme, the darkest carbonaceous objects, the primitive, ancient bodies that have not changed significantly since the early solar system, reflect as little as 2 to 5%. If you take two asteroids of exactly the same physical size and put one in each of those categories, the dark one will appear approximately 10 times dimmer than the bright one at the same distance. Now run that logic in reverse. If you observe a dim object and you do not know its albedo, you cannot distinguish between a small bright rock and a large dark one. The brightness data is consistent with both interpretations, and without additional information, both remain valid. A 10-fold variation in reflectivity translates mathematically to roughly a 3-fold variation in diameter for the same observed brightness. And that is the clean version of the problem, assuming albedo is uniform across the surface and that the object is roughly spherical. Real asteroids are neither. Many have irregular shapes, varying compositions across their surfaces, and rotation rates that change their apparent brightness significantly over the course of hours. All of that variance feeds directly into the size uncertainty. Why does this matter for impact energy? Because energy scales with mass, and mass scales with volume, and volume scales with diameter cubed. If you are uncertain about an object's diameter by a factor of 3, you are uncertain about its potential impact energy by a factor of 27. That is the difference between an airburst that breaks windows over a city and a regional catastrophe that alters geography. Both of those scenarios might emerge from identical brightness data, depending on what the rock is actually made of. The Chelyabinsk event is useful here for calibration. The object was approximately 17 to 20 meters across, a size range that would have been very difficult to resolve from brightness alone without knowing its albedo. At that size, it released the energy of hundreds of nuclear weapons in the atmosphere. Nobody died directly from the impact, partly because the airburst occurred at altitude, and partly because the main energy release was carried downward and outward rather than directly into a population center. But the zone of structural damage was enormous, and the warning time was 0. Now consider what a 50-meter object of unknown albedo looks like in a database. It might appear dim and be logged without a size estimate. It might be the brightness equivalent of a 20-meter bright rock. You observe the same number in both cases, and only radar ranging, infrared observation, or extended optical monitoring across multiple nights would tell you which scenario you are actually dealing with. The 21 objects on this week's close approach list that lack size estimates have not had that follow-up. Some of them are probably small. Some of them might not be. The database for now simply does not know, and neither do we. The solar system is not equally generous with objects of all sizes. Small things vastly outnumber large things in an extraordinarily consistent mathematical relationship that planetary scientists call a power law distribution, and understanding that distribution is essential to understanding what the close approach list is and is not telling us. The power law for asteroid populations works roughly like this. For every object 1 kilometer in diameter, there are approximately 10 objects 100 meters in diameter, approximately 100 objects 10 meters across, and so on down through the size range. The numbers are not exact. The distribution has kinks and variations depending on composition and orbital family, but the essential shape holds. Small objects are exponentially more common than large ones, and the frequency of close approaches and impacts follows the same curve. Earth is hit by small meteoric bodies constantly. Objects large enough to reach the surface and leave a crater do so on timescales of centuries to tens of thousands of years, depending on size. objects large enough to cause regional or civilizational catastrophe arrive on timescales of millions of years. This distribution creates a zone of particular concern that sits in an awkward middle range, roughly the territory between about 20 and 100 meters in diameter. Objects below this range tend to fragment and ablate in the atmosphere before reaching the surface, producing light shows and airburst events that are dramatic but generally survivable. Objects above this range, in the hundreds of meters to kilometer scale, are tracked relatively well because they are large enough to detect from considerable distances with existing survey systems. But the middle range, the Tunguska to Chelyabinsk zone, is hard to detect, partially penetrates the atmosphere depending on composition and entry angle, and carries enough energy to cause serious regional damage. The Tunguska event of 1908, which occurred over a remote region of Siberia and flattened approximately 2,000 square kilometers of forest, is thought to have been caused by an object in the range of 40 to 60 meters across. Nobody observed it in advance. Nobody recovered significant debris. The event is known entirely from seismic records, atmospheric pressure waves recorded around the world, and the testimony of people who witnessed the light and the shockwave. It occurred over uninhabited territory. Had the same object arrived 8 hours later, or on a slightly different trajectory, it would have hit a populated region of Europe. The atmosphere provides genuine protection against smaller objects. A rock under about 10 meters will typically break apart and release its energy as a fireball and pressure wave, rather than a ground impact. But that protection degrades rapidly as you scale up. Above a certain threshold, roughly 50 meters for a rocky body, somewhat larger for weaker compositions, the atmosphere is not a shield so much as a speed bump. The object arrives mostly intact, or in large fragments, and the energy is delivered directly to the surface or in a low-altitude airburst that is far more damaging than a high-altitude one. The fragmentation dynamics in between those extremes are where modeling becomes genuinely difficult. Rocky bodies break apart differently than metallic ones. Rubble pile asteroids, loosely bound collections of smaller rocks rather than solid bodies, fragment in ways that distribute energy across a larger volume of atmosphere, but also scatter debris over wider areas. The physics of these processes is understood qualitatively, but quantitative predictions for any specific object require knowing its internal structure, composition, and porosity, none of which can be determined from brightness data alone. This is the range where most of the 21 unsized objects on this week's close approach list likely reside. Not civilization enders, not harmless dust. Something in between, the zone where impact consequences depend heavily on specifics we do not currently have, and where the difference between a regional emergency and a localized air event is exactly the information contained in the blank size field. The catalog is impressive, genuinely impressive. The people who built it and who maintain it are doing something that would have seemed like science fiction a generation ago, systematically mapping the orbital paths of thousands of rocks flying through the inner solar system, calculating where each one will be decades into the future, and publishing that information openly for anyone in the world to examine. That is an extraordinary scientific achievement, and before we get into what the catalog does not show, it deserves to be acknowledged clearly. The system works. The question is where it stops working, and what lies in the space beyond that boundary. NASA's planetary defense mandate historically focused on objects larger than 1 kilometer across. This is the planet killer scale, the size of impact that would inject enough dust and debris into the atmosphere to alter climate globally, collapse agricultural systems, and threaten human civilization as a functioning whole. For that size class, the Discovery campaign has been genuinely successful. Current estimates suggest that more than 90% of near-Earth objects in that size range have been identified and had their orbits characterized to a meaningful degree. The probability of a sudden, undetected impact from a civilization-scale asteroid is low and getting lower with each passing year. That is real progress, achieved through sustained investment, international cooperation, and decades of dedicated observing time. It should be recognized as such, without qualification. But the mandate, as historically framed, says almost nothing about the population below 1 kilometer. And that is where the vast majority of near-Earth objects actually live. The size distribution of asteroids follows that power law discussed earlier. For every large object, there are exponentially more small ones, which means the catalog's success at the top of the size range represents a thorough accounting of a tiny numerical minority of the actual population. For objects in the 20 to 140 meter range, the range that includes Tunguska-scale and Chelyabinsk-scale impactors, current estimates suggest that only somewhere between 10 and 20% have been cataloged. For objects below 20 meters, the catalog captures a negligible slice of the real population. Objects in that lower range hit Earth's atmosphere regularly, producing fireballs and airbursts that occasionally make local news. Most of them were never in any database before they arrived. This is not negligence. It is important to say that clearly and mean it. The people running planetary defense surveys are not cutting corners or ignoring known threats. What the catalog's incompleteness reflects is the hard reality of what current technology can accomplish at current funding levels, pointing at the portions of sky that current geometry allows survey systems to observe on the cadence that current resources permit. Those are 3 separate constraints: technology, funding, and geometry, and all 3 would need to improve simultaneously to close the gap significantly. The cadence problem is one that does not get discussed enough in popular coverage of planetary defense. Most people assume that detecting asteroids is primarily about having powerful enough telescopes, bigger mirrors, more sensitive detectors. Those things matter, but cadence matters just as much or more. An asteroid can only be detected if a telescope happens to be pointed at the right region of sky at the right moment. Survey systems address this by scanning large areas of sky repeatedly on regular schedules, typically returning to the same region every few nights. That cadence is carefully optimized to maximize the probability of catching a moving object across multiple frames, which is how automated systems distinguish asteroids from background stars. But if an object is moving fast enough, it can cross the gap between one scan and the next without being detected in either. It is in the sky during both observations and visible in neither, because it was in the unobserved gap between them. Fast-moving, Earth-crossing objects on steep approach trajectories are exactly the ones most likely to fall through those temporal gaps. The system is designed to find most things. It is structurally guaranteed to miss some things, and the things it misses tend to be the fast, close, recently arrived ones. Orbital inclination adds another layer of complexity. Most of the solar system's mass, and most of its cataloged small bodies, orbit near the ecliptic plane, the flat disk defined by Earth's orbit around the Sun. Survey systems are optimized to scan this plane efficiently, because that is where most of the action is. But a subset of near-Earth objects travel on high inclination orbits, paths that carry them well above and below the ecliptic during portions of their journey. These objects spend significant fractions of their orbital periods in sky regions that are surveyed less frequently, in some cases barely surveyed at all. They are not invisible. A sufficiently wide field survey with enough observing time would catch them, but they are systematically underrepresented in current catalogs relative to their actual population. Fast, small, high inclination objects are exactly the category most likely to arrive with minimal warning. They are also exactly the category most likely to be missing from the close approach list entirely. Not because they are not there, but because nobody has found them yet. The Minor Planet Center, operated by the International Astronomical Union in Cambridge, Massachusetts, serves as the global clearinghouse for all near-Earth object data. When any survey system anywhere in the world detects a candidate moving object, the observation is reported to the MPC, which checks it against the existing catalog, calculates preliminary orbital parameters, and either links the new detection to a known object or assigns it a fresh temporary designation. As more observations accumulate over subsequent nights, the orbit gets refined. Uncertainties shrink, the trajectory stabilizes. This pipeline is efficient, well-run, and genuinely impressive in its global coordination. But at no point in that pipeline is there an automatic mechanism for generating a size estimate. Orbit determination and physical characterization are separate problems requiring separate resources. The MPC process produces excellent orbital data. It produces no size data at all without additional follow-up from instruments specifically equipped and scheduled to provide it. That follow-up is allocated by priority, and priority is naturally highest for objects with the most concerning orbital parameters, the ones whose trajectories, even after initial refinement, retain some non-negligible probability of future Earth intersection. Objects clearly heading for a safe miss by a comfortable margin get logged, tracked for orbit refinement, and essentially nothing else. They move through the system as orbital solutions, numbers in a database, pass through space without attached physical descriptions. The 21 objects on this week's close approach list that carry no size estimates are almost certainly in this category. Not alarming enough in their trajectories to trigger the intensive follow-up that would produce physical characterization. Not uninteresting enough to be ignored entirely. Just logged and moving, carrying their unknown dimensions through a catalog that knows precisely where they are going, while remaining largely uninformed about what they actually are. This creates what you might call a systematic filter in the data, a consistent bias in which the objects most likely to receive thorough physical characterization are the ones most likely to be dangerous, while the larger population of objects that are merely close, merely interesting, merely worth knowing about, pass through the system as orbital data only. That filter is rational given limited resources. It prioritizes the observations most critical for immediate safety assessments. But it also means that the catalog's physical characterization data is systematically skewed toward the worrying end of the distribution, leaving the middle, which is most of what flies by, as a collection of paths without profiles. What the catalog does not show, and genuinely cannot show with current capabilities, is the full population of objects in the size range that matters most for regional impact risk. Objects between roughly 20 and several hundred meters in diameter, the range that could level a city, devastate a region, or trigger secondary effects far beyond the immediate impact zone. They are out there. The mathematics of the power law distribution guarantees their existence in large numbers. The survey systems are finding more of them every year as technology improves. Algorithms get better, and more telescope hours are devoted to the search. But the fraction of that population that remains undetected, uncatalogued, and potentially on orbits that will bring them into Earth's neighborhood in the coming decades is genuinely unknown. It is not zero. It is not a number that should trigger immediate alarm. But it is a number with no reliable upper bound that anyone in the field can confidently assert. And that absence of an upper bound is itself a meaningful piece of information about where planetary defense currently stands. The space between the catalog and the complete population is where the real story lives, not in the objects we found this week, logged, and are now tracking comfortably. In the approaches that occurred while our instruments were pointed at the night side of a planet rotating away from the threat. In the size fields that are blank, not through carelessness, but through the accumulated weight of physical constraints, funding realities, and geometric impossibilities. In the rocks that flew past last year, and the year before, and the year before that, at distances well within the lunar sphere, without ever appearing in any database because the conditions required to detect them simply were not present at the moment they were detectable. 3 unsized rocks in 48 hours. 21 on the list this week, 176 within lunar distance last year, the majority of them slipping past without full physical characterization. And somewhere out there, in the portion of sky our telescopes structurally cannot survey, objects we have not yet found are following trajectories we have not yet calculated through a solar system that has been running this process for 4.5 billion years without once consulting us about the schedule. The system is working. Hold on to that. The system is working, and the people running it are doing genuinely important science under genuine constraints. But the system is not finished. The catalog is not complete, and the number of things currently flying through our neighborhood that we do not know about remains, uncomfortably, a very large number indeed.